In this video lesson, we're going to be looking at uses of determinants and inverses of matrices. And just as a reminder, the determinant of a square matrix is a value that just gets assigned to the matrix. So the determinant of a matrix is just a value. It's just a number that gets assigned to a square matrix. The way we're going to calculate the determinant on our calculator, you're going to go to the matrix menu, which is second, and then the inverse button. And you move the cursor over once to the right to math, and then option 1 is the determinant. And the first use for determinants that we're going to be talking about is to find the area of a triangle. And here's our first rule. It says the formula for the area of a triangle using determinants. You're going to be given the coordinates of 3 points that form the triangle on the plane. And you're going to call the points x1, y1 for the first point, x2, y2 for the second point, and x3, y3 for the third point. What you're going to do is you're going to put the points in a matrix, and the matrix is going to have 3 rows, but the determinant only exists if you have a square matrix. So what you're going to do is you're going to use as placeholders 1s in the third column. So you're going to take the coordinates that form the triangle, put them in a matrix. What you're going to do is you're going to find the determinant of the matrix. The symbol for determinant of matrices is just a matrix inside of absolute value bars. Or they could use the abbreviation DET, but more times than not, the abbreviation for determinant is just going to be the matrix inside absolute value bars. You're going to find the determinant of that matrix, and then multiply it either by positive a half or negative a half, depending on the sign of the determinant. And I'll give you an example or two in terms of what it is I mean. Let's look at this first problem. It says, given a triangle with the following vertices, -1, 6, 4, 7, and 8, -6, we want to find the area of that triangle. So if I make a quick sketch of those points, I have -1, 6, I have 4, 7, and I have 8, -6. And I want to go about finding the area of that triangle. What we're going to do is we're going to take those 3 coordinates, put them in a matrix. So -1, 6, 4, 7, and 8, -6. We'll put placeholder 1s as the last column of a 3 by 3 matrix. What we're going to do is we're going to find the determinant of that matrix and then multiply it either by positive or negative a half. So let's do this on our calculator. Let's find the determinant of this matrix, and we'll take a picture of what that determinant turns out to be. I typed in 0.5 times the determinant. Remember, that's in the matrix menu and then under math. I'm using the alpha zoom matrix template because I'm just going to use this matrix once and then be done. So here I'm setting up my calculator to create a 3 by 3 matrix. I'm going to enter those values in from the problem, like so, and then I'll have my calculator perform this multiplication. So when I do 1/2 times the determinant of that matrix, here I'm going to get -34.5. Well, the area of a triangle can't be negative, so instead I'm just going to make my answer positive 34.5. See, what happens is the determinant of this matrix actually turned out to be a negative number. See, sometimes when you set up your matrix, you'll get a negative determinant, sometimes you'll get a positive determinant, and that's why the rule says you multiply it either by a positive or a negative. In this case, I actually had to multiply it by negative a half, because then that negative times the negative determinant gives me a positive value for the area. So the area of a triangle can't be negative. So in this case, the area of that triangle is 34.5. So you find the determinant of that matrix that's formed by the points that form the triangle and ones as a placeholder for the third column. You multiply it by a half, and then if it's positive, that's your answer. If it's negative, you just make it positive, and that's your answer. That's essentially why the rule has plus or minus a half times the determinant. Now I wanted to show you something else. I put the points in the matrix in quote-unquote order. So I put the -1, 6, the 4, 7, then the 8, -6. But it doesn't matter the order that you put your points. Let's say I would have put the 4, 7 first, then the -1, 6, and then the 8, -6. You see the determinant would have turned out to have been a positive 34.5. Since the determinant is positive, we would just simply multiply it by positive a half to get the same 34.5 as the answer. So the key is it doesn't matter the order in which you put your points, as long as you have the corresponding XY values aligned horizontally. So let's try to find the area now of this next triangle formed by the vertices -1, 3, 4, 2, and 7, 3. So I'll take my coordinates, -1, -3, 4, 2, and 7, 3. I'll put placeholders as 1 for the third column. I'm going to find the determinant of that matrix and then multiply it by either positive or negative a half, depending on the sign of the determinant. Take a moment, enter that into your calculator, try to find the area of this triangle. Here it turns out that I have -5, so that means I would have needed to multiply it by negative a half in order to get my answer of positive 5. So the area of that triangle is 5 square units, because you can't have a negative area for a shape. So that's one use of determinants, finding areas of triangles. Positive value. Let's look at this question. Let's try to find the area of this quadrilateral that's shown. So now I'm not asking you for the area of a triangle, instead I'm asking you for the area of a quadrilateral. And is there going to be a new formula that I want to give you based on the 4 points that form a quadrilateral? The answer is no. What we're going to do is we're going to use the area formula for a triangle, just like we did that I showed you before. We'll just break the quadrilateral up into 2 triangles. So let me draw a diagonal of this quadrilateral. Now this point here in the bottom left-hand corner appears to be at the origin, so let's have the agreement, so that's the point 0, 0. First, what I'll do is I'll find the area of this left triangle that I colored in red. Then I'll find the area of this blue triangle, and then to get the area of the quadrilateral, I'll just add those areas together. So first, the area of the red triangle. Let's take the 3 vertices. Let's take, and again, it doesn't matter the order. Let's take 0, 0, 1, 2, and 4, 3. Let's use 1s as placeholders. And let's find the determinant of that red triangle, and then we'll multiply it by a half. Maybe positive a half, maybe negative a half. It all depends on the sign of that determinant. So here my calculator tells me the area is -2.5. I'm just going to make it positive because the area can't be negative. Now what I'll do is I'll go about finding the area of that blue triangle. Let's set up the vertices. The blue triangle, the vertices are again 0, 0, again 4, 3, But now we have that last bottom right-hand vertex, 3, -1. Let's put placeholders as for 1s. That'll make it a 3 by 3 matrix. Let's find the determinant of that matrix and then multiply it either by positive or negative a half, whichever makes it positive. I found this area to be 6.5. Matter of fact, when I typed this in myself, I interchanged the 3, -1 and the 4, 3. So if you would have gotten -6.5, you would have still wrote it as positive. So now the area of the top triangle is 2.5. The area of the bottom triangle is 6.5. So the area of the quadrilateral, we'll just add those two values together to get 2.5 plus 6.5, or 9. So here the area of that quadrilateral turned out to be 9. So that's one way you could go about finding the area of that quadrilateral. Now, if you would have broken up the quadrilateral the other way, drawn the diagonal going from upper left to bottom right, I kind of did the math for you, and I'll show you. Here the areas turned out to have been 5.5 and 3.5, which again, if you add them up, does give you a sum of 9. So you can use this area of a triangle formula on other types of shapes, as long as you break it up into triangles. Now I'm going to show you a use of inverse of matrices, and we're going to solve systems of equations by using inverses. And if you take a look, here we have a 2 by 2 system of equations, 2 equations, 2 unknowns. And what we're going to do is we're going to write the left side of the matrix equation as a product of matrices. Here's what we're going to do. We're going to take the coefficients of x, 1x, 3x. We're going to write those values in a matrix. Then we'll take the coefficients of the y's, 2, -6, and we'll put that in the same matrix. So this is what we call the coefficient matrix. Then what we're going to do is we're going to take the quote-unquote answers. We're going to take the solutions. We're going to take this 9 and this 3. Those are called the constants. And we're going to put those in a 2 by 1 matrix. So we took the coefficients, put them in a matrix. We put the constants in a matrix. And what we're going to do to solve for x and y is we're going to multiply the inverse of the coefficient matrix by the constant matrix. If you call the coefficient matrix A and you call the constant matrix B, then whatever x and y are equal to is going to be A inverse times B. So let me show you how we're going to go about solving this system of equations. What I want you to do is I want you to enter this expression into your calculator. I want you to type in the 2 by 2 matrix, press the inverse button, and then multiply it by the constant matrix. My advice again is to use the alpha zoom matrix template, because we're just using these matrices once and then moving on. But here, when you multiply the inverse of the coefficient matrix, remember the inverse button is the x to the -1 button, the same inverse button that you would use for numbers. So you take the inverse of the coefficients times the constants, and you're left with this 2 by 1 matrix as your answer. Well, it turns out that x is going to be equal to 5, and y is going to be equal to 2. If I take those two equations and I plug in x is 5 and y is 2, they'll check. 5 plus 2 times 2 is 9, so 9 equals 9. And 15 minus 12, that equals 3. So it really is that easy. You take the inverse of the coefficient matrix and multiply it by the constants. Let's try another one. Let's try to solve this 2 by 2 system again. First, let's set up the coefficient matrix. So we'll take the coefficients of the x's. So that's going to be 3 and 5. Then let's take the coefficients of the y's. Well, here this is 1y and 3y, so 1 and 3. So those are the coefficients. We'll take the inverse of that matrix and then multiply it by the constant matrix, which in this case is 3 and 6. So I claim if we multiply this on our calculator, we'll get the solution to this system. Take a minute, multiply this out, and take a picture of this on your calculator. And here's what our solution turns out to be. X is equal to 0.75, y is equal to 0.75. Those are both 3/4, so traditionally in math you write your answer as an ordered pair, x and y, so you can either write 0.75, comma 0.75, or you can write 3/4, comma 3/4. But nonetheless, this method works for solving systems of equations. Let's look at a 3 by 3 system, 3 equations and 3 unknowns. It's going to be set up the same way. First, we're going to take the coefficient matrix, but now there's 3 variables, x, y, and z, so let's be careful in terms of how we set this up. Here are the coefficients of our x's, 1, 2, and 1. Here are the coefficients of the y's, 2, -3, and 1. Coefficients of the z's, -1, -4, and +1. So now we're going to set up this 3 by 3 matrix. We're going to take the inverse of the coefficient matrix and multiply it by our constant matrix, which in this case the constants are 7, -3, and 0. Take a minute, enter this expression into your calculator, and let's interpret the solution. Take a picture of your solution. And here when we multiply these together, remember it's always the inverse of the coefficient matrix times the constant matrix. That's our rule. And here we get a 3 by 1 matrix, but now we're going to have the values of x, y, and z. So in this case here, our solution, x is -1, y is 3, z is -2. Seems too good to be true. Sometimes it is, but with systems of equations, this is a technique that you can use to try to solve. Try the last problem. Try to solve this other 3 by 3 system of equations. I'll give you a minute to set it up. So I set up my coefficient matrix. Always make sure that you have the signs, these values correct. It's very easy to make a careless mistake. So here we're going to take the inverse of that coefficient matrix, and we're going to multiply it by the constant matrix. So in this case, -5, 6, and 10. Take a moment, take a picture of your calculator. And if you were a little ahead of me, when you type this in, you should have gotten an error message that looks like this. See, this technique of solving a system of equations by using inverse matrices, it works most of the time, but sometimes it doesn't. If your coefficient matrix is what we call singular, what does that mean? A singular matrix has no inverse. So if your coefficient matrix is singular, if it has no inverse, then by you multiplying by the inverse of that matrix, you get an undefined situation. So does that mean this system of equations is undefined? It could be, or it could actually have a solution. We're going to learn other methods of solving systems of equations. This inverse method is nice as long as your coefficient matrix isn't singular. We'll talk more about this and other methods of solving, even by using matrices, in future lessons.